Hi class, welcome to CS360V Virtualization. This is our first class in our setup. In our setup. So we are going to have some problems as we do this for the first time, but we'll work through them. So sort of like please have a little patience. So in terms of like how the class is going to work, so I am right now on campus in a studio, and so we'll be live streaming from this studio, and the video will also be available online to watch later for folks who want to review or like missed class for whatever reason and so on. So the first thing I want to say is that like it's not required that you attend the class live. Now in the studio I can actually see sort of like a gallery of your Zoom screens, so it does help me in the sense that I can see that people are actually paying attention. I'm not teaching into a void, so it's good for me, but I do not require that either you attend or you turn on your video. I know that a lot of people have different circumstances, so it's totally fine to watch the video later or like not have your video on. Okay, so that's should be fine. All right, so let's talk about sort of like how the class will work. So there's in previous years we've had like basically 3 components. We've had exams and then we've had 2 projects. So this year we are cutting the exam, so it'll only be project based, and there are basically 2 projects. So if we can sort of like zoom in a little bit, so there will be an implementation project. Okay, so in this project you're going to be we're going to take an educational hypervisor, and what we're going to do is the TAs and we will actually rip out parts of the kernel or the hypervisor, and then we will have you fix it. And this is like super educational because like you now have to figure out like, oh, how do all these things work and how do we ensure that it works correctly. So this project will actually be broken down into a series of like mini milestones. So it will actually, in terms of like what it appears on Canvas or the deadlines, this will actually be broken down into sort of like 4 or 5 projects. We are still figuring out whether we want to break it down even further or not, but it'll be like 4 or 5 different projects, and each of them will have its own deadline. For each of them, you will be able to upload code. We will download your code and we will compile them and we will run them, and then based on that we will grade you, right? So and each of them will build on each other, right? So the first project will be something simple, and then the second project will build on the first project. So after some time we will release sort of like when we release the second project, that will have the solution to the first project, so that you can go back and see, this is what I was supposed to do, this is what I got wrong, right? So this is a very intensive hands-on project, and you will have to be comfortable with like C to some extent, and to a very, very small extent like assembly code to sort of like figure out what is going on. When students do this project, there's usually like a lot of like Googling involved because like there'll be some random assembly instruction that you have to figure out what it does and how you're supposed to do it in a virtualized environment and so on. But this will be like super educational because at the end of it, you will actually know how a hypervisor works, sort of like from the inside. So if you are interested in virtual machines, doing this part of the course will give you a very sort of like strong technical background to go to industry and sort of like contribute to industrial hypervisors. So students from this class have gone on to join, for example, Amazon's AWS kernel team. They've gone on to join Microsoft's Hyper-V team and so on. And so this is good training, but it's very hard though, like, and I will be upfront about it. So this is not a project where like, like if you decide to do it at the last moment, the results are not great. So you want to really pace yourself for this project and sort of like, absorb it a little bit at a time. Okay, so that's one project, and this will be like 50% of your grade. Okay, so there will be another one, which is the open source project. And students really enjoy this also. So in this project, you have to find an open source repository connected to virtualization. In the past, students have looked at Linux containers, Docker, Kubernetes, QEMU, and so on. and you have to talk to the developers to figure out like how you can contribute. And the way this project usually works is we divide it up into issues. So basically, if you've ever seen a GitHub repository, they have these things called issues where you can basically say, hey, like, I would like to, this is a problem, and they will be like, help wanted, like, can somebody sort of like come and help us? And then you can go in and say, hey, we are students at UT, we're working on virtualization, can we actually contribute to this? To which the students, people will actually, the developers will usually respond, and they will say, yeah, you can contribute to this is what we had in mind, and then you go off and you sort of like do this, okay? So typically, people have tackled this project in sort of like a number of ways. So by the way, like for anybody who has questions in class, do the raise hand thing on Zoom, and you can then ask questions. Actually, let's take a little break here, and I will demonstrate this. So today we have with us our TAs for the class, Ashika and Saujanya. So we will actually demo the raise hand thing with them. So Ashika, can you do the raise hand thing? Ashika, are you there? Okay, maybe she stepped out. Saujanya, are you there? If you can hear me, can you do the raise hand thing?
Yeah, I'm here. Let me do it.
All right. Okay. Let's see if it shows up on my screen. Maybe not if you're the co-host.
Yeah.
But anyway, so folks, Saujanya is one of the TAs for this class. So because our course is very implementation based, we expect that you will be, like actually sort of like asking a lot of questions to the TAs as the class goes on. So Saujanya and Ashika will each have their own office hours. So you're welcome to sort of like go talk to them about the projects and ask questions and stuff like that. Our other TA is Ashika. Ashika, can you unmute and say hi?
Hi.
All right, so this is Ashika, our other TA. So both of them are here to sort of like help you out. And like now that you've been introduced, please don't, please sort of like feel free to ask them questions during their office hours. And the way we're going to run this is, the class will be on Tuesday and Thursday. My office hours will be on Friday. Ashika and Saujanya will have office hours Monday and Wednesday. So we basically have you covered like every day of the week, basically, right? So another thing we do in classes, this class typically runs from 2 p.m. to 3:30 p.m., but we almost never take up the whole class. So I usually end the class around like 3:10, 3:15, so that students who are here can sort of like ask me questions on like Zoom and stuff. And so you don't, sometimes like students don't even need to come to office hours because they ask all their questions sort of at the end of class. All right, does it make sense? Any questions from students who are not the TAs? All right, okay. All right, so we don't have any questions, so I'm going to continue. But if you have any questions, do let me know, or like one of the TAs will sort of like pick it up, all right? Okay, so coming back to this, right? So we have the open source project, and you have to find basically issues to work on, and we will classify issues as basically easy, medium, and hard. So the general rule of thumb is that you have to do, and again it depends a little bit on like your team size, but you have to do at least like 3 easies or 2 mediums or 1 hard, depending upon the size of the issue. Sometimes the issue can be like really hard, so that like just doing one issue, getting that one thing done can take basically like half a semester. So if that's the case, then you just tackle one hard issue, right? So one thing to sort of like note here is that you don't actually have to get your code merged into the sort of like open source repository to receive credit. All you really need to do is you do a presentation at the end of the class where you try to convince me that like here's what you did, and here are the roadblocks that you hit. you try and show demos, and sometimes you can walk through code or whatever it is that you want to do. But basically the goal is to sort of like tell me about like what it is that you did, and what are the results that you got. So you submit a report, which is the details of what you did, and you do a presentation at the end of the class. So those are sort of like the two the outcomes of the open source project, right? Now, if you do in fact actually get your issue or the code that you wrote merged into the open source repository, you get extra credit. So there's actually two parts to this extra credit. So one thing which is like I use this to sort of like encourage people to do this is any issue that you get merged. It can be like a one-line thing, right? It can be like, like they forgot a semicolon, like let me put in a semicolon, submit a pull request, gets merged, you get 0.5% extra credit. It can be absolutely anything, right? And it is intentionally easy because I want you to do this, right? I want you to get into the habit of like getting your pull requests merged, right? So 0.5% for any issue that gets merged. All you have to do is you have to send me like the link to the merged issue. Then I look at the history where you say, hey, I'm a UT student, I want to work on this. Then you submit the code and they accept it. As long as I see that, you get 0.5% extra credit. Okay, this is a really easy extra credit, and I encourage everybody to sort of like take advantage of this. And you don't have to wait until the second part of the semester to work on this extra credit. You can do it starting now, right? Typically, the biggest problem students face in doing the open source project is that they have to find a repository where they feel like they can contribute. Because for most of you, right, I mean, this will be like entirely new thing, right? So you don't know where to start. It takes a lot of time to figure out, what are repositories and what are pull requests, what should I do, and so it takes a lot of time. So I highly encourage you to start working on this. So a lot of the open source project can be done in at the same time as the implementation project. You don't have to do these sequentially.
Is it? Question?
Yes, we have a question from Barrett. Barrett, go ahead.
Yeah, I'm wondering, what are the guidelines for choosing an open source repository? Does it have to be do we have to get that approved as like a systems type project, or what does that look like?
Yeah, because like the open source project is like so free form in a way, right? You will be in constant communication with me. So typically when students, when they start, they'll be like, hey, I've emailed the developers of this particular project, right? And there are a lot of projects where the culture is like very toxic. They're not really welcoming of like new people, and they like aren't very nice people overall. So we want to avoid those projects. So typically what you do is you'll send me email, right? So you'll say, hey, I'm thinking of this project, and then I can tell you like, it has, even though it has virtualization in the title, it has nothing to do with virtualization, so let's not do that. Or I can tell you, yeah, this is a good repository, and like, like the developers are pretty friendly, and like, you should go ahead with that. So you can do that.
Start that as early as you want.
Yeah, as early as you want. Like you can start tomorrow looking at open source repositories if that's what you want. And everything has to be cleared by me, right? So the repository that you're working on, the issues that you're working on. So sort of like, I mean, this has never happened in my class, but sort of like failure mode could be you show up like the last day of class with like, hey, I've been working on this project. I've never told you about this, and like, can this count? And like, this has nothing to do with virtualization. So unfortunately, right. So that could happen. I mean, it's never happened in my class, but always sort of like get everything cleared by me, right? The particular repository and the particular issues that you're working on. And it also helps to check in with me like periodically, because like, like sometimes what happens is that you pick an issue that seems easy, but then like it's like a nightmare, and you can come back and say like, like this is not working out, let me go work on another issue, and I can totally, I can say that's okay. So, be in communication with me, and it should work out.
Okay, sounds great.
All right. Did we have other questions? Anybody else? Okay, good. So, all right, so back to this, right? So we have, you pick a repository, you get it cleared by me. You pick an issue, you get it cleared by me. And people typically work on this, on both of these things in teams of like 2 to 4 people. Now, this is much harder now because like everybody's distributed and stuff. And so if you want to work on something alone, just like email me, and I've approved this in the past. But typically, like when working on things like this, it is helpful to have a team because you can bounce ideas of each other, and the brainstorming can help quite a bit, right? It also allows you to tackle like more ambitious issues. For example, if you're a single person team, you can forget about like hard issues. It won't, it's not going to be possible to do it in like the time we have. But like if you have like 3 or 4 people, then a hard is very much doable, assuming you can divide your work cleanly, and sometimes that doesn't work out also, right? So the open source project, typically you learn technical stuff because like you're contributing to a repository, but you also end up learning a lot of other things. So you end up learning how to talk to developers and how picky developers are. So getting something merged into a code base is very, very hard, right? And this is why you have extra credit. So for example, even if you did the technical thing that they wanted you to do, they will have a lot of like it has to look pretty, it has to look exactly in the way that we want, it has to follow this structure and this documentation structure and stuff like that. So it could very well be the case that you finish the technical part and then you spend like 2 weeks doing all these things to get it merged, hence the extra credit, right? So but this is something that like for most people, like when you go out into industry, this is something you're going to have to learn, right? So you're going to have to learn how to work in teams, you're going to have to learn how to work with developers, how to submit a pull request. All of this stuff like is very much required and like is good for the job. So like we can learn it in sort of like our nice sort of like friendly university atmosphere, right? So that's sort of like the goal of the open source project. Now, sometimes folks are like, like, hey, I don't want to do open source projects, I want to do something in research instead, and we can totally do that, right? So project 2 is basically very free form, right? I mean, you can do open source, and we have over the years worked out some structure for it. The research project is even less structured, but it is an option. So you can come in and say, hey, I really like this aspect of virtualization, and like I want to do some research with you on this, right? So people have worked in the past on serverless, for example. They have investigated whether like can you do these things in the serverless paradigm, like do these technologies work and so on. You can do that, right? So that's totally doable, and this will be like a very custom thing, right? Where the deliverables are much more sketchy because like like in research, like what is the output? Like knowledge, not like a pull request, right? So we will work out between the two of us like what would be acceptable to get like a good grade by the end of the semester if you do this. And again, if you're doing a research project, communication is key. Like you have to sort of like keep talking to me and telling me like hey, this is what I'm doing in the research project, didn't work out for this reason, or did work out for this reason, hey, let's do this other thing. So very free form, and like keep talking to me and we should be okay. So it's been very rare that people have taken on the open source projects or the research project and they have done badly. Usually people tend to do well, right? But just because of they are picking their own problem, and because they're communicating with me, so I lead them off rabbit holes. So people typically tend to do well, and it's a very enjoyable part of the class for them. The sort of like one common sort of failure mode is that people leave it for too late. So if like like mid-November you're picking out a repository for open source projects, like buy to extra credit, and like buy to anything harder than like an easy, right? So you can do 3 easies in like 3 weeks. It's doable if you have a lot of people, and like like I've seen people pull it off, but like you don't want to do that. Like take the time to sort of like look at the repositories early on, like pick something you like and slowly start working on it, and it'll be a much more enjoyable process, hopefully, right? So there are, I wanted to mention one other thing, because like this has happened once before. It was very nice. So we were doing a demo in class, and some students in class were like, this looks really cool and I want to build this. And I was like, there's no way you can build this. And this was like, I think like some Kubernetes demo or something, right? And I was like, there's no way you can build this in like 3 weeks. And they're like, we will do it in 3 weeks. Will you give us credit? And they actually did it. Like, and I said like, fine, do it. And like they actually did it, and like they got credit for it. So in project 2, like, like it's free form, right? I mean, if you really like some piece of open source infrastructure and you want to take a shot at building sort of like a scaled down version of it, come talk to me, and like, we can be like, okay, this is what you have to build in this time to get this credit, and we can work that out. Okay? All right, any questions so far? I have to see. Okay, so normally when I teach this class in person on campus, it's a very interactive class. That's one of the things that I enjoy most about this class, because students tend to ask a lot of questions, and like it's fun for me, right? So I would like to encourage you guys to do that over Zoom, even though it's sort of a very weird medium, as much as possible. Ask a lot of questions, and that is really, I think, what will make the class fun for everybody. Okay. Let's see. Anything else I wanted to say about the general structure of the class? I think that's pretty much it, right? So, so there's no exams again, right? There's no exams, no midterms, no finals. So everything you learn is sort of like applied. So now that might make some people uncomfortable, because if you're used to exams, this is like a really weird and new way of evaluating you, right? But I honestly think this is better for COVID times. If it's an exam, then I have to worry about cheating, and then you'll have to take proctored exams. Really not great for anybody. So we'll do this, and like if you feel like exams sort of like help you learn better, we are going to have sort of like ungraded quiz components in the class. So in Canvas, for example, if you go look at it, like like every week or so, like we will release questions. This will not be for grading, right? I mean, like your grade is not going to be affected by it, but it'll still allow you to sort of like test your understanding. And if you feel that like there's a question and like you thought you answered right and then you said wrong, go contact one of the TAs, because they are the ones who will be setting the questions. So they will know like what is sort of like your misunderstanding, and they'll be able to help you out. Okay? All right, other questions? Okay? Okay then, let's actually talk about virtualization. All right, so let's erase this stuff. Okay, so let's start with talking about what virtualization is, and like why we'd want to do virtualization. So what is virtualization? So virtualization is the act of taking basically a physical resource, right? And let's say this is like like one resource, right? And then it's turning it into a bunch of virtual resources. All right. So you have one physical resource, and then via our magic virtualization, you take it and you convert it into a bunch of different virtual resources. All right. So why would we want to do this? Because this improves the utilization of the person who owns the physical device, right? So basically, like imagine that you had like a very, very expensive resource. Let's say you have a computer, right? As it turns out in this class. Now, if you could actually sort of like give the illusion that it's not one giant computer, but actually a bunch of smaller computers, with every person then using one of these things, right? So, so now there are two things that occur, right? So in the physical resource, it might have been the case that it could be used by, let's say, only one user at a time, right? So by doing this virtualization, now you have allowed multiple users to use it at the same time. So that's one benefit. And the second benefit is it could be the case that, for example, this single user has to pay basically for the entire cost of the physical resource, right? So even if it was a computer, let's say, right? So let's say that in order to rent it for an hour, you had to pay $100. So single physical user pays $100 to rent our computer, right? Whereas in the virtual case, it could be that everyone pays, let's say, $10. Right? So let's assume that everyone pays $10, and it turns out that if you do virtualization, you can actually support, let's say, 100 users. Okay. So why is this the case? Because like it turns out that every user really has low requirements of the machine. So for example, let's say that the physical machine had like lots and lots of like cores, and this guy was actually using only like one of those cores, right? So all of the other cores were underutilized. So that's really the key thing driving virtualization. Utilization. And we'll keep coming back to this again and again, right? Why do we virtualize? To increase utilization, right? So you should sort of like get that into your head. That's really the thing driving all of virtualization, right? So, so we have like this really powerful physical computer, and we rent it to like, this guy for $100 per hour. But it turns out this guy is actually using only like, 1% of the resources that are actually available, right? So if there was a way for you to sort of like divide up this physical resource in some way, you could actually support 100 users, right? Now, this guy is not going to pay $10,000, even though he's only using 1% of the resources, right? So there's an economics argument in here, right? So this guy, even though he's using 1%, is not going to pay like the full cost of the server, right? So if you ask him to pay $10,000 per hour, he'll be like, no, not going to do it, right? Whereas if you then sort of virtualized your resource, and there are like a number of these virtual resources, and you can support 100 of them at a time, each user paying $10 per hour to use these things, now you can see that your resource is fully utilized, and as the owner of this resource, you are now making more money, right? So higher utilization now directly means more money for the owner of the physical device, right? For the person who is renting out, it's also a good deal, right? Because like previously, they were paying $100 to access this resource per hour. They didn't need that much. And so like for a scaled down version of this physical resource, now they're paying only $10 an hour. So it's a win for the provider, and it's a win for the consumer, right? Does it make sense? This is basically Amazon AWS, by the way. So this is Amazon. This is all like virtual machines you can rent on Amazon, and the users are us. So this is like a real world example, even though sort of like it's highly abstract, right? Does it make sense? Any questions so far? Okay. All right. Sorry. Feedback. All right, so I'm going to leave this up, and I'm going to move to slightly different parts of it. Now, one of the main sort of like benefits of computer science is that we have virtualization, right? So if you can imagine, right, like astronomy, right? How do things work in astronomy? So you have a hill, and then you have a really powerful, really expensive like telescope out to look at the heavens. And then if you go talk to astronomy grads, they time share this really, really expensive resource, right? So basically it will be like, like from 1 a.m. to 2 a.m., like, Jennifer is going to access it. And then from 2 a.m. to 3 a.m., Bruce is going to access it, and so on, right? So the way that they share this really expensive resource is via a very coarse-grained method of time sharing, right? So you can have only one user at a time, and that user gets the whole resource. This means that there are only a set number of users you can accommodate per day and per year and so on, right? So if you divide it up in terms of like 1 hour, there are only 24 users you can accommodate in a day, even if you're asking grad students to go there in the middle of the night, which they do, I think. So this telescope is not being virtualized very well, right? Whereas in contrast to that, we have our giant supercomputers. So for example, if you're in Austin, we have like our Chameleon clusters. If you go to TAC, they have like tons of supercomputers. And even though this is a similar, extremely expensive and powerful resource, we can actually have lots and lots of users at the same time, right? TAC doesn't say for 1 hour I'm giving it to a student, like the next student come back in another hour, right? They don't restrict the supercomputer use to 24 users per day, right? So virtualization is really the key reason why computer science has sort of like burst in efficiency, right? Every other graduate student on campus has to actually go to lab to do research. Like we can do research from our home. And part of the reason why we can do that is because we are very, very good at virtualizing stuff, right? We don't actually need to be near our expensive physical resource. We can access it via virtual resources, and because of that, we can all work from home, right? So virtualization is actually sort of like a very key thing, even though it's sort of like a technical thing in CS, in sort of like if you look at broadly our history, it is really one of the reasons why CS exploded and why sort of like we are in the current situation today where we can sort of like work from home even in the middle of a pandemic. So it's all sort of like due to virtualization, right? Now, virtualization has been happening for like a really, really long time. Even though like we'll learn about like very new things in class today, it has been happening for a long time, right? So if you look at this, the cycle, so the very first computers that we had, like things like, for example, well, let's actually start from ENIAC. So things like, like the ENIAC supercomputer that was there back in the day, these things had time sharing. So you could submit jobs, it would do one job at a time, then you would get the results back on punch cards sort of like later, right? So very coarse-grained virtualization in the sense that like, like multiple users can use it, but it's time shared, like only one user is running at a time. So from there, we went to sort of like, like smaller things, like for example, the PDP-11, which is where, like the C language, for example, and Unix were developed. This was sort of like a thing that you would put in your office. But again, this was a very expensive resource, and basically, you had to control who had access to this resource at different points of time. So we're still at time sharing, right? But then after that, we had this notion that you could basically have your supercomputer, and then people would have what they called thin clients. So what does this mean? This means that it's basically our computer labs of today, right? So you have a monitor and a keyboard. But you don't need a CPU. I mean, even though in our computer labs we do have one, you don't need a CPU. The user would basically use the monitor and the keyboard to connect to the highly efficient supercomputer, and there can be multiple of these users at the same time, right? So even though the supercomputer was there, you're no longer doing time sharing. Internally in virtualization, you are doing time sharing in a way, and we'll sort of like get to that in the next classes, but at least from a user's point of view, you're not doing time sharing. many users could access the computer at basically the same time, and the users did not have to care about how many other users there were. Whereas in the telescope example and the time sharing example, you always knew in a schedule, hey, like Bruce, you are at 2 a.m., I am at 3 a.m. So you knew there were other people, you knew there was contention, and you knew that's why you got the 3 a.m. slot. In this case, there is actually, like, you don't have to worry about anybody else, like, unless you're running some giant program which is crashing everybody's computer. But you don't have to worry about anybody else. It is as if like you had private, exclusive access to the supercomputer, right? So this was really the start of virtualization as we knew it today, right? So, and if you have taken undergrad OS at UT, for example, like you already have learned all of this stuff, right? You in undergrad OS, they talk to you about like how do you virtualize a CPU, how do you virtualize memory, right? You virtualize a CPU, like via time sharing, for example, different programs. It makes it seem as if they're all running at the same time, but only one of them is running on the hardware at any given instance. You virtualize memory through page tables. So everybody is given their own private view of memory. It seems as if you have sort of like infinite memory, but really like you access it via page tables. That's how you divide up memory. How do you virtualize storage? You are given sort of like partitions, like sort of like home directories, for example, and whatever is in your home directory, you can do whatever with impunity, but you can't touch the home directories of other users. So this is how we have virtualized sort of like our giant supercomputer into sort of like smaller instances that each person can access and not have to worry about what other people are doing. So operating systems today already have virtualization. They virtualize the CPU, they virtualize the memory, and they virtualize storage. So it's all already happening, right? But this was at a level where you wanted to allow multiple people to sort of like access the same machine. But they all knew they were different users in the same setup, and they were all basically running the same software. Right? So in this particular setup, they all had the same operating system. Right? So everybody if you go to our computer lab, the department runs the same OS across all of these machines. They're all sort of like synced together, and like it's the same operating system. And if somebody causes a problem and sort of like crashes the supercomputer, everybody loses access at the same time, right? So there is the notion that one person, if they're malicious, can affect another person. And the next part of virtualization sort of like fixes this stuff, right? So now we are moving in history again, and now we have virtual machines. Okay, so the idea here is that we have our giant supercomputer, and let's say that it has, to make up a number, 500 cores, and then it has 500 terabytes of DRAM, and let's say 5 petabytes of storage. I think to be a respectable supercomputer, you need specs like this, right? So you have all of these things, and what we're going to do is we're going to give to each user the illusion that they have a smaller machine, which we are calling a virtual machine. Okay, now this can have, for example, 2 cores. It can have, let's say 4 GB DRAM. I can have access to, let's say, 1 terabyte of storage. I'm pretty sure if we went on Amazon, we can find a virtual machine with these sort of like exact specs, the T3 Nano or something like that, right? So now, once you have this virtual machine, you are master of this virtual machine, right? You can run a different OS. So for example, let's say that your supercomputer is running Linux, and for some reason you needed Windows, you could do that. right? So your virtual machine could be running Windows and your supercomputer can be running Linux, right? Even more sort of like interestingly, if you crash your virtual machine, your supercomputer does not go down. In fact, a lot of the stuff we learn about is to provide very strong guarantees that regardless of what you do inside your virtual machine, you are not able to affect the actual supercomputer, right? So there's a very strong protection guarantee. So virtual machines provide isolation. Okay, it's a key property that virtual machines provide, which other virtualization technologies do not provide. So if you want isolation, virtual machines are your target. That is what you should get. And we learn all about virtual machines in this class. So we'll talk about like how they function. You know, how do you have memory inside a virtual machine? How does CPU work inside a virtual machine? All of this stuff we're going to talk from basically next class onwards. Okay. How are we doing on time? Okay, so we have about 20 minutes more. So let's see. All right. So virtual machines. So when they came out, right, they were a revolution, basically, right. So prior to virtual machines, if you are running a company and like you have accountants and graphics people and whatnot, right, what you would do is you would buy machines and you would buy desktops and you would give basically to all of these people and say, run Photoshop or run whatever accounting software you want, right? So everybody basically got a machine, or like a group of people got a smaller group of machines and so on, right? So it was very expensive and very underutilized, right? Because like, the accounting people are not going to be fully using the machine at all times. And whereas the graphics people are like, hey, it would be nice if you had another machine, but like no budget. So this happens a lot, right? So when virtual machines came out, what private companies then started doing was they would buy basically a private cluster of like really beefy machines, right? Not quite supercomputer scale, but like, for the time at least. Like this is basically early 2000s. Okay, they would buy like really beefy machines. And like what they would do is then they would basically give a virtual machine to one to accounting, another to marketing and so on. And if the marketing people are like, hey, like we have to do this like really important like ad campaign push, it would be nice if we got more resources, then you're just like, hey, take another virtual machine, like because you have spare capacity in the underlying physical machines, right? And then like if your company is downsizing, you can get rid of all of the marketing VMs, absolutely not going to affect anything. So you now have the ability to allow people to spin up virtual machines whenever they want, to basically use whatever operating systems they want, and you can size these things appropriately. So you can have slimmer machines for accounting, much more beefier machines for marketing, for graphics, and so on. So you are able to take the investment that you put in, like your group of beefy servers, and turn it into sort of like a fungible commodity, right? Even though you have like, let's say 8 beefy servers, now you're able to turn them into however many virtual machines you want with very different specs according to what your company needs. And this provided like so much flexibility that for a lot of companies, if you go look at them today, like for example, if you go to like a realtor or something, right, they will actually access their company internals or the network via a virtual machine. So on their machine, they will be actually having a virtual machine running, and they'll be like you're logging into the virtual machine and using that to access their company internals. So it's become a very widespread sort of like thing, right? And there are a number of like opportunities and challenges with doing something like this. So one opportunity is now like basically for IT folks to basically say like hey, you need to patch your computer with all these safety updates. They can just take these virtual machines, apply these things, and then give them back, right? So these are all sort of like virtual commodities. So the IT people have access to them, and they are able to sort of like run updates and do everything. Whereas previously, like, it was like much harder to do all these things. So that was one thing. but it also introduced the problem that now that people could run their virtual machines, you could have a virtual machine sleeping for an arbitrary amount of time, not receiving any updates whatsoever, so that one day it comes back up, it has a lot of vulnerabilities, and then attackers are able to sort of get in. So it's both a security opportunity and sort of like a nightmare. So as with many things. Did we have any questions? Okay, no, okay. Anyway, so virtual machines, when they came out, were really revolutionary and changed a lot of things in the industry, based on how people were using the physical resources that they had, right? So the journey continues, right? So we keep moving forward. Okay, so this is now 2005, late of the decade. And now what people were realizing were that virtual machines were great for isolation, but they're very heavy. To run a virtual machine, you need several, at least megabytes of DRAM. You need to allocate some amount of your physical resources to it, like your storage and so on. And they were this is not great for all of the use cases that we want, right? So for some use cases, you really want the security that comes with it. But in other use cases, you don't really want all of these things. And sort of a big use case that came along where virtual machines were sort of a poor fit was software development. And the specific problem that software development had was packaging. Another way to call it is dependency hell. So you have an application that you have built, okay? Now let's say your application is called A, right? Now A actually depends upon B, specifically version 1.3.4. It's a library that A uses. And then you need another library C, version 2.4.6. Okay. Now, the problem that developers were facing was that when you sort of you write your application, you whenever you want to deploy it, you need these exact versions of the software, right? People were running into this problem where they would deploy them on a customer machine and they would have a different version of B or C, and then it just wouldn't work, right? Even though everybody wants backwards compatibility and all of that, it just wouldn't work. So because of this, what people started doing was basically packaging B and C along with A and then sort of distributing it to people. Wouldn't it be nice if there was an easy way to sort of do this, right? And this is where the container was born. Okay. So the container is a virtualization technology, very similar to virtual machines, but it is lightweight, right? So you have your physical machine at the bottom, and you could run a bunch of these containers. And sort of in contrast to virtual machines, if one of the containers is doing something malicious, it now has the ability to bring down the whole machine, right? So you don't get the same isolation that you get with virtual machines. So if a container does something bad, all of the other containers on the same physical machine can be affected. Okay, what you get in return for this is that containers are really light. So you can have containers that are 1 to 10 megabytes in size. Okay, so it is entirely possible to basically say, hey, I have a container image, and then I'm going to send you this container image. When you run this container, inside you will find the applications that I developed, and it already has all the correct dependencies built in, it's compiled, it's working. Start the container, run this application, right? So it's very, very easy to sort of write software in this way, package it as a container, and then send it off to people, either for testing in sort of different environments or directly to your customer. So Docker was really born at this time as basically this way to package up your sort of software and then ship it off to people, right? That's hence the name Docker, right? And if you look at the logo of Docker, it's really this ship with different containers on top of it. So that's really the analogy they're going for.
Vijay?
Yes.
We have a question.
Yes. Sorry, Barrett, go ahead.
Yeah, so you said that containers might be anywhere from, or not anywhere from, but containers might be just a few megabytes. And I'm wondering what kind of application, like is there some example of like a large application that you think would reasonably be packaged into a 1 to 10 megabyte container?
Right. So, for example, let's say that you have been developing like a game, and the game does not have a lot of like images or associated resources that are heavy. So, in this instance, you could imagine the game being like a couple of megabytes. Now, the container does not add more than a few more megabytes, so that the whole thing is like less than 10 megabytes, and you can ship it off. If you were to use a virtual machine to ship your game, it would be too heavy.
Okay.
Right. So that's sort of like the idea. Did we have other questions while I'm at the podium?
There is a question in the chat section.
Okay, let me check. All right, so how are burstable VMs implemented? AWS T3, for example, is designed for low utilization across many customers, inefficient if each user will be given a single physical CPU. So we'll get to that, right, as to how burstable CPUs are implemented. But the idea is that you have some minimum set of resources that are sort of like given to you, and every sort of like VM is definitely has minimum resources, right? But you can expand those resources, and it could be the case that, you know, like depending upon other utilization in the same physical machine, those resources may be denied to you, right? And we will talk about like, you know, like oversubscription and how virtual machines sort of like adapt to that. There are very interesting things like balloon drivers, where basically the way oversubscription will manifest itself to the virtual machine is like there's some application which is using a lot of memory, so you want to, you know, kill it, and that in turn actually sort of like gives a lot of memory back to the physical machine. So we'll get to that in a little bit, and we will cover how burstable VMs actually work. Right? All right. Other questions? Okay. All right. Back to our board. Okay. So containers. The reason that containers are sort of like, you know, really lightweight is that they don't have their own OS, right? So in the case of a virtual machine, you actually, inside the virtual machine, you are running a copy of a different operating system, and because of that, it's very heavyweight. Containers use the operating system of the underlying physical machine, and because of that, they are light. But now the problem is that, like, if you want to run a Windows container on a Linux machine, you can't really do that. You need the OS that the container expects and the OS of the physical machine to match, right? So if you want cross OS support, that's something where you really need a virtual machine to do it. Okay, so we will be learning all about containers again in sort of like different parts of this class, and you know, like again, like you're free to do your project on any one of these things, right? Okay, so moving even further in terms of like, you know, history. Okay, maybe I should erase something. Look, I think we have it covered. So then we have the idea of like serverless. Okay, so the idea in serverless is that we are on a journey where we reduce the granularity of virtualization, right? So for a virtual machine, we had basically an entire machine as the abstraction. For a container, it's a container which is like basically a group of applications. It has the same underlying operating system. With serverless, the idea is that it's a function. You have a function and you want to run it on like, you know, like one of like let's say Amazon or Microsoft servers, and you want the result of the function. You don't really care about whether it runs in a container, it runs in a virtual machine, or it runs on a physical machine. You want this function to be executed, and you want some way to get the result. Okay, this is what is called the serverless paradigm, where in containers, if you run containers, for example, on like Amazon, whenever the container is running, you are going to get charged. Right? Now container is much more lightweight than a VM, but still like, you know, like, so you can run more containers, but you're still going to get charged whenever the container is running. In the case of serverless, you only get charged when the function is executed. So serverless is a really, really good fit for use cases where for a long time you're not really going to have any activity, but you have a lot of activity near one date. So imagine, for example, an online store which sells things only for Valentine's Day, right? So if they ran using containers for like most of the year, they're not going to get any activity, you're just going paying money to Amazon for no reason. With serverless, come Valentine's Day, they will get a lot of activity, and then these functions will get triggered and they will get charged for that, right?
I have a question in the chat section.
Yes. Does function mean a function in a programming sense or in a math sense? They are pretty similar, but in a programming sense. So basically a Python function, for example, or JavaScript function is sort of like what we're talking about. There are a lot of like limitations for serverless functions. So the serverless function, for example, typically cannot actually store any state internally, right? So there can be, the idea of like a global variable doesn't exist. So if you're familiar with like functional programming, it's a function of functional programming languages. If you take a Haskell function, for example, it's sort of very similar to that. So the serverless function has all of its state is external, right? So it can, for example, read from a database and then like answer a query and then store the answer back in a database, but it does not have any sort of like inbuilt storage, and once the function execution is done, everything associated with the function just disappears. So you can't really use it for any stateful processing, right? So for example, imagine that you had a function where every time the function was called, a variable was incremented, right? Now, in order to do that in the serverless paradigm, you need to store that count in something external, like a database. If it's a variable inside the function, it's going to get lost, right? So serverless has a number of like limitations, like it doesn't really work out very well for like all cases. Like for example, I have friends in the industry who complain to me that, you know, like serverless is like really hot right now. So there is this trend where they take everything and they try to fit it into this serverless paradigm. It doesn't really work, right? Because the serverless is good for some things and bad for others. So if you really try to fit something that doesn't work in the serverless paradigm, it's added complexity for not really like a lot of gain, right? And when we talk about serverless, like later in class, we will actually go over like, you know, what is a good fit for serverless, and you know, like what is not a good fit and so on, right? So we'll be ending the intro class soon, but like one thing I really want to emphasize, right, is that this is a very fast moving field. So this is the third time I'm offering virtualization. Every time I offer this, the field has already moved. And every time near the end of the class when I talk about serverless, for example, Amazon and Microsoft have done something new, and there's something new that we have to cover, right? It's very, very cutting edge. What this means is that it's a great opportunity for you guys, right? You can build something that has a lot of impact. You can do research that's really cutting edge. It's not sort of like, you know, like we're learning stuff from 30 years ago and like, you know, like everything's been decided. No, like it's actually right now, right? And a lot of things that we take for granted, people do stuff and then show that they're not really true. For example, we have said that like, virtual machines are heavyweight and like, containers are lightweight. There's a paper called Light VM that we will be learning about in class, where they show that the virtual machine under certain circumstances can be as light as a container, right? Like a few tens of megabytes in size, right? So we have these micro VMs that are now becoming more of a trend in the industry, right? So now it seems like virtual machines can be light. Like, okay, what else can change? So a lot of these things are like really new and changing all the time. And you could be actually having the insight that changes or has the next phase in this sort of like virtualization journey. So don't take the stuff I teach for granted. These are not like set in stone. You could, for example, figure out a way to make virtual machines like much more lighter or much more efficient or something, right? So these are all like moving targets. Okay, and that's sort of like what I want to emphasize. All right, we will actually stop here for today's intro class. I'm happy to take questions about the material or about organization of the class and stuff. All right, but if you have other stuff, you are free to sort of like leave at this point of time. Other questions? Yes, go ahead, Barrett. Or was it an old question?
Okay, I'm ready to ask. I was just going to say, I thought the first class went really well, and I just wanted to make sure that you had that feedback since you don't really have
Thank you.
the classroom. But the pacing was good, and the delivery is good. So I appreciate that.
Thank you. And I do encourage people to sort of discuss on Piazza. So we have about 90 students in class, and one of the very nice things about a class this size is that you learn from each other, right? Especially near the end of the course, where I am covering material that's been out 6 months, so I'm not really more of an expert than you are. I just looked at it before. So you just you have to sort of learn from your classmates, and I think Piazza is a very good tool for that. So make sure that you ask questions and you engage with your classmates.
Yeah, absolutely.
Mm-hmm. Other questions?
We have a few questions in the chat section.
All right, in chat. So some people said they couldn't hear anything, but that's later. Okay, I'm going to go from the back. All right, so what would you say is the working definition of virtualization for this class? I think you basically go back to here. You're taking a physical resource and you're multiplexing it and sharing it and showing it as multiple virtual resources to different users. So that's the essence of virtualization, basically. All right, where does JVM fit into this picture? So the Java virtual machine is similar to what we have been talking about, but it's not as big an abstraction as a full virtual machine. So the Java virtual machine, what it gives you is the ability to run bytecode on different hardware, and it abstracts out the differences on the Java virtual machine. So if you have learned about a hardware abstraction layer in undergrad, it's basically similar to that, right? It is doing virtualization, but for basically only one thing, instead of all the different components of the system, right? Okay, all right. Right, so I mean, people have asked questions and I have answered, for example, I've run Linux Docker containers on Windows, how does that work? Well, Windows has a particular subsystem to enable you to do that. They have basically parts of Linux running inside them. Let's see, okay. All right, let's see, anybody else? Okay. All right, it looks like I was muted for a while, but then that got resolved. All right, any other new questions? Just went through that list. Any other questions about projects and how stuff will be graded and stuff like that?
You mentioned that there's different steps to project one, and they're going to be released progressively. Are the dates for that going to be put on the schedule?
They are. So we're working on the split right now. So hopefully we'll have the split of the projects and the dates. They'll be due pretty soon.
Thank you.
Yeah. One thing I can say in that respect is that the first part of it will be due about 2 to 3 weeks from now. And then 2 weeks later is the next part, and so on and so forth. All right. Other questions? How will the projects be graded? So for the I guess the implementation projects, there will be very strict guidelines. So we'll be when. Well, one of it is that your virtual machine has to run at the end of the project 4, but there will be other things we will tell you exactly what we're checking for, and you can run those tests yourself to make sure that it is working correctly. So project 1 will be very strictly defined. So there are tests that we will give you to make sure that hey, indeed you are passing this and so on. So that should be very strictly defined, and you will know how you're doing on that project. So that should be. That should be clear, I think. Project 2, it's much less clear. And you'll have to talk to me to find out, basically. All right. other questions? What's the size of the group? If you mean for your projects, between 2 to 4 people. Again, like if you want to work on it alone, email me and I can approve it under certain circumstances. Yeah, but I encourage people generally like the 3-person team seems to work the best. And so like this is a conversation I have basically with every group that takes virtualization, and it's like I'll be like, you're a 3-person team, and like they're a 4-person team, and like they should be able to get done more. And the 4-person team will be like, no, like that doesn't actually work, and like the work does not divide evenly, and so on. So you'll find out basically like every person you add beyond like 4 is like diminishing returns basically. So like I mean I would recommend a 2 to 3-person team. I'm okay with 4 people. Beyond that, it has to be like I have to look at it to see if it makes sense and approve it. Yeah. Is a browser tab considered a virtual machine? In the sense of like Chrome, yes. So in Chrome, what is happening is that every tab is a different process. So it has its own address space. So if that particular tab crashes, only that tab crashes. The whole browser does not crash. And incidentally, this is why one of the reasons why Chrome takes up a lot of memory. It's a giant memory hog. Whereas with other browsers like Safari and Opera, the whole thing is basically one process. So there you don't have quite the same level of virtualization. Yeah. All right. Let's see. Other questions? I was really glad that people sort of like replied on Piazza, introduced yourself. It's always nice to get to know my students. And we have like a very nice, diverse class. So I'm really glad. Yeah. All right. Okay, so I think we will basically stop here for the virtual for the stream. I think I'd still be available. Like if you want to, have questions over email, for example, email them to me. And like the TAs are also there. Like and Piazza, you can post a question as a private question, so only I and the TAs can see it. And then you can ask questions about the class and stuff, and we can do that. Okay. All right. So with that, I think we will end today's class. Be safe, all of you, and I will see you on Tuesday. All right.